and the webinar is being recorded for later viewing. If anybody would like to answer or ask any questions, we'll take those at the end, and if we run out of time, I will look to get back and consolidate any answers following the distribution of these notes. So if you could please use the comments box, and we'll summarise them at the end. So good afternoon, guys, and thanks again for taking your lunch break out for this webinar. With respect to the presentation for a zero emissions operations within the port environment, we have myself, Mike Hennessy, Group Technical Authority for Associated British Ports. I've been with the business 19 years as a trained electrical engineer, and the reason for the discussion today is really to tackle or address some of our challenges that we've got in the business within the shipping industry. Really, there's a commitment to go carbon neutral by 2050, and quite interesting on that topic is that only today, really, early last week, the UK government published its delayed national infrastructure strategy, which is quite a timely reminder of what we need to do and the challenges. So to kind of combine topics today, we've got shore power as a solution, and also kind of the option for energy storage systems. And I guess the challenge within the engineering fraternity is to kind of combine them moving forward to maximise the output of that. And outside of that as well, we've all got our own challenges, but some may not be in our control, such as power demand, infrastructure capabilities. So hopefully this will give a bit of food for thought on that. So that's myself. Next introduction is Luca Imperiali. So Luca is going to guide us through the shore supply elements. Luca started his career after graduating from electrical engineering and worked in ABB research. He then operated as a systems engineer in Milan prior to then joining ABB as a project engineer in 2008. His involvement spent the last 9 years detailing and have been involved in shore connections, which will gain some valuable insights today. And then following from that, we have Thomas Tengnier, who is a global product specialist in energy storage, and Thomas holds an energy systems engineering qualification and is a co-author of a Polaris ice breaking study, which some of you guys might want to look into after that. So that's the introduction from me and today's speakers. If I can hand you over to Luca, and we can start the webinar. Thank you.
Thanks, Mark. So, welcome everybody to this webinar on how ports can reduce their environmental impact. My part will cover let's say, the general introductive part and the part on the shore connection. So, why ports need to be greener? Why ports need to be smarter? Because there is a general awareness now that climate changes are a huge cost for communities, and there are many technical solutions, many possibilities that allow to a port to reduce the impact of their activities. In order to be more functional, all these activities, all these initiatives need to be taken in a holistic way. So, in order to coordinate all this effort to get the best and the maximum result out of this. One of the characteristics of a port that reduces its impact on the environmental is the capability to integrate with the state-of-the-art technology different features. So ports are no more simple an industrial area, but are a place where the last development in terms of technology are used to, again, reduce the environmental impact of activities. And in order to do so, port need to integrate into its own grid, electrical grid infrastructure, the shore connection, meaning the capability to feed vessel when they are at berth, but also have smart charging system that are capable of charging electrical vessel and electrical vehicles, and at the same time to integrate source of renewables, so wind, solar, and other source of power that can further reduce the power demand from the existing grid. So in order to do so, a port must start to see its own grid no more as a normal system, normal bunch of loads. That is the traditional way of thinking a grid, a utility grid. But start to think a grid as something smart, a grid that is flexible, that can change its configuration, that can integrate source of power and eventually energy storage. We, as ABB, we have identified 5 areas where we can support the port to become smarter. One is the traditional, what we consider the traditional shore connection. That is basically the possibility to, for traditional vessels to stop the engine when they are at berth and take electricity directly from the port grid. Port electrification, that means reducing all the diesel crane or diesel engine that are present in the port and replace them with electrical engine. Increase the capability, the port integration, so integrating renewables, energy storage in order to optimize consumption. The e-mobility, that in our case includes not only the e-vehicles, but also hybrid and battery ferries. And of course, a global system of service for the whole port. So port can be seen as an ecosystem, a large ecosystem that interact with the rest of the world, with the city, with the distribution and electrical distribution, and that have the ability to integrate different things inside. So energy, renewables, electrical activities, shore power, and everything. Again, in order to optimize and to reduce the footprint of a port, we can propose a set of solutions that are coming from our R&D, that are also coming from our sales support in order to optimize the CAPEX, OPEX result of the port, and so on. But why a port wants to use shore connection? Why a port is looking for port electrification? Because the main part of, because an engine that is burning fuel, especially a vessel at berth is burning heavy fuel, is creating pollution. So there are a lot of emission as NOx, SOx, or CO2 that are coming from a vessel at berth, as well as vibration and particles. Shore connection is the solution for all of this. We can, some of the numbers, especially related to the cruise industries, but also other type of vessel have similar characteristics, are quite impressive. One vessel at berth is capable of polluting up to 2,500 equivalent cars. So having a cruise vessel in a port means having 1,000 of vessels in that area. We know that cities are doing a huge effort to improve to reduce the pollution coming from vehicles. They are moving towards electrification of mobility. So the next step in this direction is to allow the vessels that are at berth to switch off their engine and feed directly from the port electricity. There are already some, this problem is already been identified at a global level, so not only at local level as European or North America, but also at IMO, that is National Maritime Organization, as one of the biggest biggest impact of navigation. So there are areas where it's already now mandatory to switch off the onboard engine and to connect to the port grid, as some area of Baltic Sea and some area in North America. The benefit for a port that move into this direction, and experience is coming from ports as Los Angeles and Long Beach that since very long time ago have decided to move into this direction, but other ports could be Göteborg in Sweden or Bergen or Oslo, is the reduction of the emission directly from the activities in the port, and this is achieved with through port electrification and through shore connection. But also it's increasing the appeal of living near portal area, because the moment that you switch off the pollution coming from the port, also the real estate near the port are increasing their value. And this makes easier for a port to carry on their daily activities. So there is less pressure from the population towards the activities, towards the existence itself of the port. What is then shore connection? Shore connection is the possibility to connect the vessel, the electrical system of a vessel, to the onshore grid. In order to do so, we need to make available the electricity that is available onshore, similar to the one that is on board. So in many cases, we need to adapt the voltage and the frequency. The whole system is designed mainly in general with an electrical substation, usually a medium voltage substation, a distribution towards the different connection point on the berth, what we consider the mechanical interface for the vessel, the cable management system, the system that allows the flexible connector to go physically on board. And then, of course, the system on board, the interface panel and the control system that allow a seamless transfer of the load between the ship and the shore. So basically, shore connection is designed in a way that the vessel doesn't even feel that there is a switch between the onboard generation and the onshore generation. There are different type of vessel or different type of application for shore connection. Probably Ro-Ro and Ferry is more widely used here in Europe. Container vessel that is more used in US, in West Coast. Cruise vessel that is now moving from US to, let's say, from US West Coast to East Coast, and now also to Europe. Some specific application for some vessel that LNG on tanker or floating storage unit. This is also a very interesting application. So basically floating storage that are permanently at berth that use electricity instead of their own engine. And of course, traditionally very used since very long time ago is shoreside electricity for shipyard and navy. one of the key requirements for shore connection is to have a full interoperability between the ship and the shore. So, wherever the vessel is built, it must be able to connect in US, in Canada, in Mexico, here in Europe, in every different country, China, Japan, etc. And this is possible because there is an existing framework of global standard. So it's a triple logo standard. It's an IEEE, IEEE, ISO, IEC standard that define all detail of the interface between ship and the shore for high voltage shore connection in medium voltage basically, and the low voltage shore connection. There is in addition a standard that define how to integrate ship and shore in a more smart way. So we know we are able also to deliver systems that have higher degree of automation with limited number of people around to operate the connection when the vessel is when the connection is established. Different type of vessel requires different amount of power, but to some extent also some different voltages. There is as such a standardized low voltage shore connection that can fit vessel with 400, 440, 690 volt. In this case, we are facing vessels that have consumption around 1 to MWh and frequency that can be both 60 and 50 Hz. There is the segment of Ro-Ro and ferries that is characterized of 11 kilovolt shore connection. There is the segment of container that is a little bit different from Ro-Ro and ferries because in this case the voltage is lower and the connection is done with 2 plugs. There is the segment of cruise that is quite well established in ports as Los Angeles, Long Beach, San Diego, Vancouver, Seattle. Nowadays there is also Halifax, Brooklyn, and we will see Hamburg, Malta, La Valletta, and other ports also in Europe. There are some special application for, as we said, LNG and tanker, again using 6.6 kilovolt. And then there is the tailor-made segment of shipyard and navy that is a little bit less standardized, but also because here there is no need for a fast and quick connection. But we are talking about more the in industrial system design. Cruise vessels are usually the most important type of shore connection. We are talking about 20. Sorry. This is a cruise, we were saying about cruise shore connection. Here we are talking about up to 40 or 60 MWh, 20 MWh for vessel. It's a very important facility, and this is probably the most demanding segment in shore connection. Example of this are you can see here an example of typical shore connection, one for one single vessel, or facility that allocate more than 2 vessels. We can be flexible. We can design systems that allocate up to 6, 7 different vessels at the same time. Another segment is the one very well used nowadays in US, in Los Angeles, Long Beach. It is practically mandatory that every vessel that docks in Los Angeles, Long Beach, container vessel, use this shore connection facility. In this case, the installation is a little bit less demanding. We are talking about 7.5 MWh per vessel, even though we know that the vessels are requiring definitely less power. The solution can be dedicated for one single vessel or centralized. In this case, we need galvanic insulation for each vessel. The onshore, it's different from the cruise because the cable management system onshore there is basically nothing on the berth. There are only pits with plugs with the sockets, and there is the vessel that have the cable management system. So it's typical of container vessel to have the cable drum on board. Example of this are these two. One is a single connection from one single vessel, and the other one is a centralized conversion for more vessels at the same time. In some cases, since the container vessel are not always requiring all this amount of power, it's possible to optimize the solution using a smaller facility, so optimize the OPEX of the port accordingly to their own need for the specific type of vessel that are talking. Further typology of shore connection is the one for Ro-Ro and ferries. Basically, in this case, the vessel is connected usually with a crane, what we call a cable dispenser. And one of the characteristics of Ro-Ro and ferries is that since all these vessels are in low voltage, they have already galvanic insulation on board. So a facility, one single facility, can feed many, many vessels. In this case, one single facility can feed 50 and 60 years vessel up to 5 vessels at the same time. And then there is this new segment that has been it's developing in the recent years. It's low voltage shore connection. In case of low voltage shore connection, the cable management system can be fixed or mobile, and the whole substation is 1 or 2 MWh. One of the characteristics is that since the power is limited, we can design a system that is easy to fit in, easy to plug in into the port, and that can be limited to one single container. So with one single container of high cube standard container, we can allow the connection of the vessel to the port grid. And finally, there is the most innovative segment, and this is also the part where I will hand over to the next speaker. And it's about the use of energy storage, because this segment is the one for AC or DC shore connection, but they are targeting vessels that are using hybrid propulsion or are completely electrical vessels. A characteristic of this vessel is to have batteries on board and to use the shore connection not only to allow to switch the engine on board when they are at berth, but they need to recharge the batteries. So the whole infrastructure onshore, it's a little bit designed to optimize, to allow this function. So there are batteries in many cases also onshore in order to reduce the impact on the grid. So the grid doesn't need to provide the full amount of power, but at the moment of the shore connection, but can charge the batteries during the time that the vessel is not present. And this again, with this we go again to the question of port that must be smart. So here, apart from the batteries that are of course one of the most important component of this solution, both on board and offshore batteries, but the most important part is the control system, the management of these batteries, how and when we discharge these batteries, and how we interact with the rest of the grid. Because once again, the target of our solution is to allow a port to be greener, but limiting allowing them to carry on their normal activities, to be more efficient without renouncing of the normal industrial activities. Okay, so this is all from my side. Thomas? Hello?
Hello?
Yeah.
Sorry, I had some issues to unmute, but I think, do you hear me now?
Let me Okay, that's all yours.
Thank you. Thanks for the good presentation and introduction. I think maybe there were some more slides that were on your part, but we can jump over those.
Yeah, some references of what we have done in the years. So some a list of reference that we have delivered all around the world, and some specific cases that show that shore connection can actually be used in many different ways. So again, okay, all yours now.
Okay. So I think about energy storage in the port environment, and the focus of today is the onshore batteries or energy storage solutions. So just to start, a little bit look into what is happening in energy storage, not only in ports but in general. And what you can see here, this is a forecast of stationary grid-connected energy storage system deployments by Bloomberg New Energy Finance. And as you can see, the expected growth in this area is really large. And what we have today is basically nothing to the volumes expected in just a few years. These two graphs show installed power per year, and that it is a ratio between power and energy of about 3 to 4, so meaning that of course there will be installations that are optimized for short duration high power applications, and others that will be designed for a lot more than 4 hours, like it could be intraday energy shifting and things like that. Yeah, energy storage can be integrated in many different parts of the grid. It can be integrated into the generation units, like thermal power plants, in order to optimize those. It can be installed close to large load centers, as spinning reserve and so forth. But for ports, this would go into the category of industry and large commercial installations, where the energy storage can be used for a variety of functions. Then, of course, we also have the transportation, and really the automotive industry is the really driver for reducing the cost for lithium-ion battery technology, and that benefits all other applications will benefit from that push from the automotive industry. So they are in let's say the driver's seat for getting the necessary investments in battery production capacity and so forth. And that brings down cost by a lot. Yes. And then, of course, ABB Marine and Ports, we are also offering the onboard hybrid solutions, including batteries. But as I said, today's focus is on the stationary side, the port side. ABB, we have offerings that cover most of the listed use cases on the stationary side, from standardized pre-packed energy storage solutions, wayside energy storage for rail applications. We have UPS lineup, as well as the onboard batteries, both for marine and for rolling stock and rail applications. I just wanted to say a little bit about the technology of the energy storage. So, I mean, energy can be stored in many different ways. A decade ago or so, it was quite a lot of interest in high temperature sodium sulfur batteries and things like that. And the reason was basically that lithium-ion batteries were more than 10 times more expensive at that time than what they are today. So basically, lithium-ion has seen a tremendous development, both in cost and also in energy density, as well as energy efficiency. So all these factors speak for lithium-ion, and that will certainly be the dominating energy storage technology going forward for at least a decade or so. After that, it could be so that solid-state batteries, possibly also lithium-based, but not today's technology, could become competitive, but that remains to be seen. And it is still a lot of improvement potential in lithium-ion batteries. So for the performance measures, the energy density, of course, is very important, as well as that in some cases at least, also power density can be relevant. And then cost and expected lifetime. If you look at the different battery types that are available, lithium-ion is really shining on most parts. So this is what we are discussing basically when we talk about energy storage in this context. So what is the challenge in a port, and how can energy storage help address that? Well, the load profile of a typical port may be a container port with a lot of things, or a very small ferry connection, but with an electric ferry that is being fast charged. It is a very fluctuating power profile with very large power peaks. And peaks do cost money. So looking at the energy bill or power bill, if you like, of any grid connection, it is constituted by the connection fee and the demand charge fee, as well as the consumption fee. So the consumption fee basically is the dollar per kilowatt hour, or the cent per kilowatt hour of used energy. But then on top of that, you have also costs for how much power you take. And if you can reduce your power peaks, you can also reduce both the red and the green segment in this cost. And ports, they are often, if it is large ports, they are often located close to city centers or close to large cities. And due to the urbanization, cities tend to grow, and the grids becomes more and more congested. So increasing your power demand may even be impossible, because there is simply enough power that can be fed into the city. Because I mean, it's limitation in power lines and so on that can be pulled into the city. So that is one thing, that it may be a lack of power in those places. And also for much smaller ports, that may have a charging connection for an electric ferry, for example. Such vessels are often operated in rural areas, maybe going to islands with very weak grids, and to have the energy and charging time requirement met, you need to have very high charging power. And that, again, can then be addressed with an onshore battery. And then, of course, if you have this very short but high peak loads, that also brings up your demand charge fee and also the grid connection fee, meaning that your operating cost becomes high. So also you can manage your OPEX by utilizing energy storage for peak shaving. So yes, basically that is what I said in the last slide. But energy storage can be used for more functionality than that. It can provide a stabilizing function, reducing the load change or rate of change of your demand, providing better voltage stability, for example. It can provide backup or spinning reserve power to your port. An energy storage system connected to AC is connected to power electronic converters that can also provide STATCOM functionality. So phase balancing and reactive power compensation. Well, the most important, or let's say lowest hanging fruit, obviously, is the peak shaving functionality. So here, one example is a project we have in north of Norway, where we have a few fully electrified vessels that are operating a connection between Vennesund and Holm. This is remote and with very weak utility grid. And here we could only get 300 kilowatts of power from the utility grid, while the charging power required for the vessel, the most demanding energy requirement condition that happens during summertime, when you have a little bit of rough weather during summertime with very high intensity schedule as well. Then you may at some points need 2.8 megawatt of charging power. The charging time available is only 9 minutes to meet the schedule of the vessel. And the energy per trip is up to 350 kilowatt hour. So this in a way put the framework of what to achieve, and the solution we came up with there was to install a buffer battery of approximately 1.37 megawatt of lithium-ion batteries. In this case, those are integrated in an e-house on shore, and the vessel is charged with DC, 1000 volt DC. That was and this is, I would say, quite typical solution for as a buffer battery for ferry charging for electric ferries. Sorry. Okay, example here is a container port, and what you see is a typical daily load profile of such a container port. We have, as you can see, very high peaks, but the container cranes, they also regenerate power. And I'm not sure about these port specifically, but in many cases it also makes sense to integrate renewable energy sources into the port grid itself, such as wind power. Typically, ports are next to the shore where you have very good wind conditions, and it is already an industrial site. So it's quite favorable to integrate wind in ports. In this case, I do not believe it is actually wind integrated, but in that case also you get the variability in and power fluctuations caused by the intermittency of wind, and then all the intermittency in load. And the peaks that we see here, it's up to 3.6 megawatt. That is regenerative power coming from the cranes. And then we have also very large demand peaks of approximately 9 megawatt hour. So in order to address this, if an energy storage system is considered, then it would provide peak shaving to manage this and to reduce the demand charge levels by a lot. So the idea is to, when the battery is integrated, the orange segment here is addressed directly by the grid connection, while what you see in blue is managed by the energy storage system. But when you have an energy storage asset, you can actually tap into more revenue or value streams as well. So this is from a report done by Rocky Mountain Institute, where they have identified different grid services or services and potential revenue streams for an owner of energy storage system. And in principle, all that is within this red part of the cake could be addressed by an energy storage system integrated into the port. So that means also the port could play in the utility grid power, let's say, service market, and provide, for example, frequency regulation to the grid, and by that get additional revenue. So here is one example. This is a quite fresh study from IHS Markit, where they have looked into how BESS systems connected to a utility grid with, let's say, functioning market mechanisms for providing such services, how it plays, and what different functionalities provide revenues. So what we can see here is that frequency regulation is a quite profitable service to give. You see that you get steady revenue streams every day. And one important or interesting thing here is also that because they provide the frequency regulation, they can decide to provide frequency regulation just in one direction, but still get paid for it. So they have no cost, more or less, for charging their battery. They charge for free and get paid for it, because they do this frequency regulation. So basically they charge exactly when it is favorable for the grid to do it. And then they have some energy shifting or also day ahead energy trading that can be done, and in some cases that can also provide additional revenues to such an energy storage system. So this should also be considered when considering to invest in energy storage also for a port. So this is just an example illustration of how an energy storage system can look like. This is aimed for being fit into a 40 feet container. You have one part that are the battery side with Typically, lithium-ion batteries in the voltage range of 11 to 1200 volt, fully charged, and then coupled with power conversion systems, filters, and normally the transformer is placed outside of this container or gas. Yeah, that's what I had to share today.
Excellent. Thanks a lot for that, Luca and Thomas. I see we've got a question or two up the side. I guess just from my point of view, prior to just diving into the questions as well. Obviously, quite a real challenge, and I get from my experience within ports. I think it's trying to justify a business case as well. So there's always the investment model and the ever-changing customers, which kind of trying to bring these two together, combined with perhaps constraints on the grid, is trying to realise that. And I think obviously the government are also realising that in the recent announcement I mentioned at the beginning of the presentation, and they've committed to funds as well to really kickstart this. I guess Thomas and Luca, in terms of your experience and opportunities, is a business case always a large problem in trying to kickstart a lot of these projects? Just hand over to Luca if any comments on that.
Yeah, the business model is, this depends a lot, country by country. There are basically many voices involved in this, in the question of the investment for shore connection as well as for energy storage and so on. In some cases, the business case is, I don't know, for example, there is a common business case that is common to e-vehicles, e-buses, and electrical ferries. For example, if the existing grid, the vessel has a stop or a berth in a location where the existing grid is very weak, there is a benchmark between the investment between adding batteries and reinforcing the grid. So having a new substation, in some cases high voltage, low voltage substation, etc. This is quite, it's a business case that we can consider quite simple. But in the main part of the cases, there are many things to be considered. In many cases, there are funds. In others, there are policy on the battery, on the cost of electrical energy. There is also, it is very important also the pressure that there is on a port to adopt this sort of measures as the shore connection. And we know that, for example, the model in Los Angeles and Long Beach that is mainly referred to the shoreside electricity for container vessels, that basically the port is free to develop, to enhance their activities if they adopt this sort of measure. So there is a sort of balance between the need of the port to expand industrially and the need of the collectivity, so to reduce this. But we can help our customer to provide business case, but this is really depending case by case.
Yeah,
a lot.
No, understood. And I kind of just looking into the questions, for presentation slides, I'll look to, we are recording this, but I'll look to upload where possible on the IET Humber LinkedIn site, and then reaching out to Alex Parsons-Holt. Do you think that electricity will win out over hydrogen solutions, or both will continue to grow within the sector? And I guess that probably relates to my question as well. Where's the future? Where's the business case? I think it's probably, from my point of view, a balanced decision based on a number of factors such as infrastructure, investment opportunities. Hydrogen is taking quite a play. It's becoming quite a player in the energy solutions. Is it the future? I think that's my opinion. It's probably balanced at the minute. I don't know if Thomas or Luca have got any thoughts on that.
Yeah, I think there will for sure be room for both. So battery electric solutions will always have an upper hand in terms of energy cost. So generating the hydrogen will, the efficiency of doing that, you lose quite a substantial part of your primary energy when producing renewable hydrogen. And as such, if you have a ferry, for example, that can be addressed with batteries, that will always give you a lower operating cost in the end. But there are so many vessels that will not be, that it will not be realistic to electrify them just by batteries. So hydrogen will have a very important role to play in the future, and it will certainly be a balance between this, and exactly where that balance ends up, it depends very much on technology development, and it is a bit difficult to predict really. It's both on the hydrogen side and on the battery side. It is a lot of promising development going on. So let's see. It's an exciting future.
Yeah, I absolutely agree. And kind of this isn't the solution, and this is why it was chosen as a topic of discussion really, because we're engineers, and it's about using best available technology to provide solutions which are forever growing. And I think the matrix of vessel sizes and capacity demands quite puts that into perspective really. So just mindful of the time as well, so we've got 4 minutes left, so I'll just have a look through the other questions. So Ash McDougall has raised the question of, do ABB provide in-house revenue optimization of their installed systems? So it sounds like that's a continuous review in terms of a support arm with respect to their solutions. Perhaps one for Thomas.
Yeah, maybe I can bundle these 2 questions from Alex and Andy together. So regarding the environmental aspects of battery production, basically. There have been multiple studies, and it is a continuous flow of LCA studies for battery electric cars versus gasoline cars. And in those applications, it appears to be so that roughly 2 to 3 years of use is required to pay back the additional environmental cost for producing a battery electric car versus a gasoline car. But that also will change because all the assumptions are based on that we are using, when we are mining the minerals and so on, we are using today quite polluting grids with a lot of coal power and so. But it is also a very clear shift to more renewable energy in the grid. And as the grid becomes greener, also the minerals that we use or that we extract will be greener as such. So I think in that regard, it will only get better with the future. And then for electric vessels, we use the batteries a lot more intense. An electric car is, or any car, is parked roughly 96% of its time, or something in that range, meaning that the batteries that are in an electric car is really underutilized. In marine applications, typically the vessels are operating continuously, and we are charging as quick as we can to do the next trip and so. And as such, those batteries are used a lot more and pay back their investment cost also very much faster. And that is even, I mean, we have one reference LCA study we did for batteries on a hybrid OSV vessel, and there the finding was that it would be paid back actually within a month.
Okay.
Or something in that range. I don't remember exactly the number of days. I think it was 37 days or something like this, to pay back the environmental cost for producing the batteries.
Okay, that's quite interesting, and I know there's been other discussions outside of this forum relating to the same, so very, very relevant. Okay, guys, I'm just mindful of the time, and I think we've answered most questions. Any that we haven't, I'll look to kind of wrap up on and get out to the attendees list part of that. So thank you for joining the event, and more importantly, thanks to ABP for hosting that with in conjunction with the IET, the Humber network. I hope you found it of use. Just a notification of the next IET Humber local network is a week today. Challenges of a manned mission to Mars, Wednesday the 9th of December at 7 o'clock in the evening, so hopefully you can join us for that as well. Again, thanks to all, and look forward to speaking to you soon. Thank you.
Thank you.
Thank you.
Thanks a lot, Thomas. Thanks, Luca.